Locked and lost genetic variation, talk about selection goals, and then end by answering how do we get there. So to start with, really the impetus of this talk was a paper by John Cole, who just got done talking. And what he and one of his colleagues did was looked at what are the selection limit estimates in dairy cattle if we start putting all the best parts of the genome together. And they did this for Holsteins, Jerseys, and Brown Swiss. And they looked at it from two different perspectives, and we'll talk about both of these perspectives. One is we're just going to reach in and we're going to pluck out the best chromosome from an individual cow and see if we stack all the best chromosomes in a breed together, where could we get? So that's a picture there. You can see you've got a chromosome. A chromosome is just one giant long strand of DNA that's supercoiled and wrapped around some proteins, which Dr. Britt talked about earlier. So the second option, so that's kind of our lower limit, if you will, of potential genetic improvement. The other option is to pluck the best genes out of the genome. Like we have a picture there of a gene, and that's part of that chromosome. So if we pluck the best genes out of the chromosomes and stack them all together, what is the potential upper limit for some of these selections? And so let me just go through an example here. This is actually a chromosome by chromosome PTA for milk yield for Evergreen View, my 1326 ET. Now I know she's no longer the world record holder, but this was a slide that I generated a few years ago in class. And the Council on Dairy Cattle Breeding used to produce these, and you could go in and look at your cow's breeding values on a chromosome by chromosome basis. They've got a lot of other things going on, so it's not a high priority for them at this point, and they haven't redeveloped this yet. But what we have here is in blue, this is what my 1326 inherited from her sire. And then that orangish color is what she inherited from her dam. And so what we're considering here is, can we pluck the best one of these and pass them on to our offspring? So if you look at the first chromosome, so we're on the far left here, my 1326 had a genomic PTA for chromosome 1 of basically plus 250 pounds. And about half of that came from her sire, and the other half of that came from her dam. If you go to chromosome 3, you can see now she got a favorable contribution from her sire of plus 125 pounds, but actually a negative contribution from her dam. So we want to pluck what she inherited from her sire and leave what she inherited from her dam behind. You can kind of see the same thing if you get further down the list, chromosome 23. So basically this lower limit, what we're asking is, if we take the best stack from each and every chromosome and put them all together, what would our potential milk yield PTAs look like? Now, the problem is that getting those best together is quite a long shot. Okay, so if you bought a $300,000 heifer, for instance, and you were hoping to get the best, you'll get really good, but the very best probably is a little bit out of your reach, because you basically, at each chromosome, we have a 50% chance of inheriting the best haplotype from either our mother or our father, if you will. So we take 1/2, multiply that together 30 times, and that gives us 0.000009%, which is another way of saying 1 in a billion. Okay? With bulls, it's double your chance. It's actually only 1 in 500 million, because the sex chromosome, there's only one option. If it's a daughter, they're going to get the X chromosome that was inherited from the mother. Okay, and that assumes that there's no recombination involved. So that just kind of gives you a sense of the likelihood of some of these things happening. So let's look at what we have in terms of milk yield for our upper bounds and our lower bounds. Okay, so we are expressing, all of these I'm going to be expressed as estimated breeding values. So an estimated breeding value is a measure of a cow or a bull's total genetic merit. We express in our bull proofs, we express genetic merit as half of that number, because we're worried about how much genetic superiority a bull will pass to its offspring. So we take that breeding value and we divide it by 2. So these numbers that I'm going to show you, the estimated breeding values, are basically the PTAs for these traits multiplied by 2. And you can see we've got our 3 breeds represented there. And the first thing that I want to point out is that the Holstein has the most potential, both from a lower bound and upper bound perspective of those 3 breeds. The reason for that is simply that there are more Holsteins. We have more variation available. There have been more Holsteins genotyped, so we are able to capture a little bit more of that genetic variation. And so when we look at the lower bounds for Holsteins, we could get an estimated breeding value on the lower end of 25,000. So that's plus 12,500 in terms of a PTA value. And on the upper end, we're looking at close to plus 80,000. So a PTA for milk of plus 40,000 pounds. All right, so let's think about what this would look like if we start to add that to what our cows can do today. So we're going to look at 2 cows here. So on the left, we have Aftershock 3918 and then My Gold over there on the right. And both of those cows happen to have an estimated breeding value for milk currently of about plus 1,000 pounds. So if we take Aftershock 9318's 78,000 pound world record, we add that to the upper bound of genetic potential in our population, we've got a cow that could produce 150,000 pounds of milk according to our genetics. At the upper end, the lower end would be plus 100,000 pounds of milk. On the right, we basically get the same answer. 150,000 pounds of milk on the upper end and 101,000 pounds of milk on the lower end. So that's kind of our genetic potential. That's pretty exciting when you think about where we are now, where we could go. So switching gears a little bit to daughter pregnancy rate, we can see again, Holsteins have more potential than Brown Swiss and Jersey, just because more have been genotyped and there's larger population. So Holsteins on the lower end, we're looking at a daughter pregnancy rate estimated breeding value of more like 40%. And at the upper end, now you can start to see, well, wait a minute, there's some things that maybe just don't add up quite right. Now we've got 140%. So that basically means the cow's getting bred the moment she calves and conceiving. So maybe the bull calf, she has a bull calf, he can do it on the way out. Don't use a beef bull. All right. So, but again, enormous amount of genetic variation that we have if we start to put these things together. And then lastly, we have our estimated breeding values for net merit that were explored. And Dr. Cole mentioned this a little bit yesterday, plus 7,000 pounds on the lower end, plus 23,000 pounds when we look at, or pounds, dollars, okay, plus $7,000 on the lower end, plus $23,000 on the upper end. And then in blue, I've kind of put the largest values that we have currently, and that's basically plus $2,000, a little bit more than plus $2,000 is our lowest, or excuse me, is our highest currently. So we have a lot of room to make genetic progress for lots of different traits. So let's kind of look at what one example. Oh, I forgot, I have a couple things that pop up before I get to my next slide. So our current rate of progress is about $150 to $160 of lifetime net merit a year. So at that rate of progress, it's only going to take us 46 years until the lower limit is reached. In a century and a half, we'll get to the upper limit. Okay, now, the good thing about prognosticating way into the future is that you're not gonna be, no, I'm not gonna be here and be around if I'm wrong. So I can tell you whatever I want to tell you, and then, 50 years from now, nobody will know the difference. Okay? But so, we made a lot of progress over the last half century, and look what we maybe could do over the next half century as well. And this doesn't really address the question. I'm not going to talk a lot about crossbreeding, but I'll mention it here. What if we start plucking the best from each and every breed and begin to synthesize genomes from multiple breeds? And that is certainly being discussed in some of the scientific communities as well. And we just don't know what those limits are. Okay, so here's an example of a cow that would have an estimated breeding value of net merit for $20,000, so plus $20,000, and a PTA of plus $10,000. So if we get plus 60,000 pounds of milk, that would be a PTA of plus 30,000 pounds of milk. And if we add that to our current average mature Holstein cow's milk yield, that gives us a cow of about 88,500 pounds of milk. We get about plus 3,000 pounds for fat, which comes out to a 4.6% fat test at that 88,000 pounds of milk. 3,100 pounds of protein at 3.6%. And then we hold the line on everything else. So our fertility doesn't decline, our productive life stays the same, somatic cell score stays the same. That would be a cow that would be toward that upper limit of lifetime net merit. All right, so can we get there? I don't know, but that's the type of cow that we would be looking at to get there. Of course, we don't just select for milk yield. We select for lots of different traits. And so this slide here just shows you the correlation of a bunch of traits, all the traits that are part of lifetime net merit. So fat yield is the most highly correlated trait with lifetime net merit at about 0.7. Somatic cell score, obviously we don't want higher somatic cell score, so that's negatively correlated at about negative 0.3 or so. And milk yield has a negative weight in lifetime net merit because it's strongly correlated with both fat yield and protein yield, the correlation there is actually positive about 0.45 or so. Okay, so we can take those numbers and we can calculate our expected progress as the correlation that we see here times the genetic standard deviation of the trait times the total amount of net merit change that we want to make. And I'm not going to show this for all the traits, but I'll show it for a few. If we look at that $20,000 net merit cow, we're looking at a milk yield somewhere between EBV between 11,000 and 36,000 pounds of milk, fat yield between 600 pounds and plus 2,100 pounds of milk, a somatic cell score at our current rate of progress at the lower limit. So let's just say the average cow is about 2.5 or so now, and we make a -2 progress. Now we're looking at a somatic cell score of only 0.5. And then obviously, if we look at the upper limit, we start to see, okay, well maybe these genetic limits aren't quite the same as the true biological limit. Because now we've got a upper limit of -7. Well, obviously that's 0. We can't go less than 0 somatic cells. All right, and you can look at body weight composites, also interesting. At the lower limit, we're getting close. We're basically halfway between a Jersey and a Holstein size currently. And at the upper limit, we're milking goats that give 80,000 pounds of milk. Okay, so there are genetic limits and there are biological limits. Eventually, you run into a wall. And we want to talk about those walls here just a little bit and how do we discover those. Some of those are obvious. We can't get below 0 somatic cells in a milliliter of milk. We can't get above 100% reproductive efficiency. Others aren't quite so clear. Here's an example of running into the wall. So these are the Kentucky Derby winning times since 1900. And you can see there was a pretty steady decline until 1950, and then it's basically been flat since then. Secretariat is the lowest dot on that list. He was in 1973. He set his records. And some scientists have calculated how fast we think a horse could run, and they think that record could be broken by 1.5 seconds. So we can see this flattening out here. And what's interesting is that if you look at genetic merit for racing speed in thoroughbred horses, they are genetically, they can run faster than ever before. The average is improving. So Kentucky Derby times averages are improving. If we look at just any random race around the country, the average is better now than it has been. But the top times are not improving. So they refer to that as Cunningham's Paradox. So what are our Cunningham paradoxes? I don't know. Sprint times for thoroughbred horses are improving, but these types of longer distance races are not. So what is the biological limit? Well, here's the thing. We won't know until long after we've arrived. And even then, we may get some new genetic variants that pops up that actually expands our biological limit a little bit. So this is a chart from many of us would consider the Bible of quantitative genetics to be a book written by a geneticist named Faulkner. And this was from his book. And he's showing a long-term selection experiment in mice. And he's weighing his mice. And he selected one line to get bigger, one line to get smaller. And you can see that they diverged until about 20 generations. And then it flattened out. But if you look at that top graph there, after 40 generations, all of a sudden it bumps up again a few grams. So that was some sort of new mutation or recombination that occurred. But in most species, you are going to hit a wall at some point. Potential yield limits, it's hard to know. Maybe it will be a limit to the nutrient intake of our cows. We know that bigger cows can eat a little bit more, so maybe over time, our cows will get a little bit bigger to have more digestive capacity, but there's going to be a limit to where we can get. And in fact, we know that if we have cows that eat more now, all we do is pass the feed through her more quickly and don't digest the feed as well. So we're already kind of hitting a little bit of a digestive limit to some extent. Metabolic capacity, if you've ever had a cow with fatty liver syndrome, you exceeded that, not you, that cow exceeded the metabolic capacity of her liver to process ketones. You know, how much blood can our dairy bowlers now are probably finished competing their championship roundups, and if we ask them how much blood it has to flow through the udder to make a pound of milk, they would all be able to tell us. I don't know the answer to that though. But there's a limit to how much blood a heart can pump. And then udder capacity. Maybe more frequent milking can help overcome that to some extent, but that's a potential biological limit as well. So next I want to turn our attention a little bit and think about locked and lost genetic variation. And what I'm going to show you is that some favorable genes are physically linked to unfavorable genes, and we have to have recombination to unlock that type of thing. So Dr. Cole yesterday talked about genetic hitchhiking, so that's what he was talking about. And we may have some really good genetic variants that are lost from a population and we'll never even know they existed. In fact, I'm certain we've already lost some good genetic variants. Okay, and to me, this is the real problem with inbreeding. It's not inbreeding depression. It's what did we lose that maybe in the future would have helped us a little bit. So it's kind of a short-term versus long-term problem. So we're going to start here. I just want to show you a look at passing chromosomes from one individual to another. And I stole this slide from Paul Van Reyden. And this is a bull named Megastar who was a double grandson of Aerostar. So if we start in this upper right-hand corner, that orange line that you see there is what Aerostar inherited on chromosome 24 from his sire, who happened to be Starbuck. So that's what he inherited from Starbuck. That blue is what Aerostar inherited from his dam. And then we're looking at what did Aerostar pass to Megabuck. And you can see Aerostar passed on his entire chromosome 24 to Megabuck without any recombination. Okay, Megabuck's dam, on the other hand, there was a single recombination event. He got part of his maternal grandsire's haplotype and part of his maternal granddam's haplotype. Then we go down and we look at Digny, who was a German cow, and Aerostar did the exact same thing, passed on that entire chromosome 24 with no recombination. Digny's dam had a double recombination event, so we can get 0 recombinations per chromosome, we can get 1, we can get 2, we can get 3, we can get 4. In this particular case, in terms of the Aerostar chromosome, we got 0. Then we look at what happened to Megastar. Megabuck passed on that entire chromosome 24 with no recombination. Digny did have a little bit of recombination right at the very end. So that's a little bit of inbreeding on chromosome 24 for this particular bull. So now let's think about this, how this works in terms of losing genetic variants for us. This is just a section of chromosome with 5 genes. And if we've got an arrow in green pointing up, that means it's a good gene. And if we've got an arrow in red pointing down, I'm really sorry if you're red-green colorblind. I wasn't thinking very well when I did that. But arrows pointing down, that's an unfavorable gene. So what we'd really like to have segregating in our population is a section of chromosome where everything's great, and the other option is everything's terrible. And then we know what to do. We get rid of that bottom chromosome there with the arrows pointing down, and good riddance to that genetic variation. We lost genetic variation, but we didn't want it. But that's usually not our choice. What happens if these are our 2 options? So now we've got on the top 4 good genes, and we've got our lousy gene locked in with those 4 good genes. And then on the bottom, we've got 4 lousy genes with the good gene locked in there. Our genomic prediction methodologies at this point are not able to identify that as something good that we want to keep. So that's basically going to be lost. So we've lost some genetic variation. So if we really truly want to reach our selection limits, we need to come up with ways to capture some of this genetic variation before it's gone. One potential way to help out that a little bit, we'll talk about some Holstein Pulse article from Dr. Lawler. We could actually potentially maybe even select for higher rates of recombination. And if we do that, we would break up some of those unfavorable hitchhiking, if you will, a little bit more frequently. There's still a lot of work to be done in that area to know how it's related to other traits and so on, but that is one potential area where we might be able to help release some of that genetic variation a little bit more reliably. Okay, I'm going to shift gears here a little bit, and we're going to talk about how selection goals will continue to evolve. So when we're thinking about the ideal cow of the future, this is where we get to, we really don't know what she's going to look like. So this is just TPI in 25 versus 2017. Basically, half of our emphasis was on fat and protein in 25, and now it's more like, say, 35, 40%. And we've shifted it. It used to be more protein relative to fat. Now they're a little bit more equal. Rather than daughter pregnancy rate at 5%, we now have our fertility index at 13%. And then there are additional traits that we didn't have before: feed efficiency, livability, daughter stillbirth. So the point here is that our selection goals are going to continue to evolve. So what traits are going to become more important in the future? And I put a question mark after all of these because the reality is that we don't necessarily know, and that we're going to be speculating at this point. I think based on our last talk, one that's probably very likely is that we're going to do more precise selection for feed utilization. We do some indirect selection for feed utilization now. We select for cows that give more milk. They're going to eat more. They need feed in order to do that. So we do select for feed utilization to some degree, but we'll get better at it. Properties of milk. I think this is going to be a big one. And you heard that presentation this morning about milk and human health and so forth. I think we're going to move away from worrying about fat percent and protein percent and start asking ourselves what fatty acids are being produced and how do those fatty acids impact milk processing and human health characteristics, and what types of proteins are produced. So that picture in the upper left, that is an scanning electromicrograph of a casein micelle. So that is the basis of a cheese curd, if you will. So can we start, and we know that there are different processing characteristics associated with different genes. Right now, we kind of crudely do some of these things a little bit with beta casein and kappa casein and so forth, but there are many genes involved. We could actually get PTAs for milk processing and capabilities and for healthiness of the milk and so forth. So I think that's going to become something that's more important. Immune function. So we do a little bit of this now with Immunity Plus from CMEX, but I think that we're going to see that expand a little bit. And in fact, when we look at the genomes of old lineages of cows versus new lineages of cows, that's one area of the genome that's changed. Parts of the genome that are related to immune function have changed. Now, that doesn't automatically mean that what's changed is bad, or that what we've changed has been bad. Maybe we've made good changes to the immune function of the cow, but we don't really know, and that's something I think that will become more important. I already talked about recombination just a little bit. That's something that we may select for. Just genome structure in general. I think one of the lessons from the genomics era is that we don't really know a whole heck of a lot about genomics. We know the DNA sequence, and that's about it. But when you start to look at some of the advanced technologies, people are now starting to look at how the genome is spatially oriented in the nucleus of a cell. And part of the epigenetics that Dr. Britt talked about probably relate to how it shifts where that genome is located in the cell. So really cool stuff that we may be able to select for in the future. Stress resistance. So Australia now has genetic evaluations for heat tolerance. I think just stress and resistance in general may become something that we select for more in the future. Precise cows for precise management systems. We have robot-ready bulls now, but that data is it's rather indirect. I think we're going to start to get data from robotic milking systems to build genetic evaluations for cows that fit into the robot. And that won't just be for robotic milkers. That'll be for region of the country, region of the world, lots of different things. What we're going to feed those cows. So I think in the end, what that means is that probably when we talk about the super cow, if you will, there's not going to be a super cow. There's going to be lots of different super cows. Additional functional traits like hoof health, mobility. One area we're working on is, what about cows that don't get treated with antibiotics? We already have our organic market. They don't treat their cows with antibiotics. We expect that pressure to continue to increase. So selecting for cows that are healthy without some of those tools will become more important in the future. And then I think environmental sustainability is something that's obviously a very hot topic, if you will. So I could be wrong. There could be others that are more important, but those are some of the things that I think about anyway. Then the last question I want to address is, how are we going to get there? We've got a century and a half. Boy, that's a really long time. Are there ways to get there faster? Well, one of the ways that a lot of scientists are excited about is gene editing. And gene editing is suitable for traits such as that are controlled by one gene, such as horn versus poll and the slick hair coat and A2 milk and so forth. Traits like milk yield are, I put the word infinitely more complicated, and I did mean infinitely when I put that in there. We actually call some of our models the infinitesimal model, where we say that there are infinite number of effects affecting a particular trait. And that obviously that's not quite true, but the more we learn about the genome, the more we realize that our models are actually near infinite at least. So we're going to need advances in genomic methodologies. So we're already doing some whole genome sequencing, and that's helping us to find areas of the genome that are important and incorporate them on our chips for genotyping. Certainly, RNA differences among individuals, we'll start to scan for those. And I think more of a functional understanding of the genome is also important. So yesterday you heard about, we got a scorecard on our genomics. I didn't calculate our GPA, if you will, based on Dr. Lewhouse's scorecard, but I don't know if I would accept those grades into my graduate program at Penn State. So, and one of the areas that was really bad was understanding the genome and how it works. And we really, other than the DNA sequence, we really don't. And so we tend to, right now, when we look at genes and SNPs, we look at them as kind of their own little island, doing their own little thing. But the reality is there's not a gene in our genome that can do anything by itself. It's all part of an interactive network. It's an entire organism working together. So trying to understand that, it's really difficult to wrap your head around. Some other ways that we might get there: advanced embryo production technologies with embryos as parents of embryos. Rather than a 2-year generation interval, maybe we can have a 6-month generation interval. That is something, the type of idea that excites scientists. It doesn't excite me as a breeder, because then that's completely taking breeding out of the hands of the breeder and putting it to somebody in a white lab coat. So whether that's good or bad, I don't know, but it's something that's certainly being discussed. Right now, we don't have the capabilities of doing that, both from an embryo production standpoint and from a genomic standpoint, because now we're looking at embryos that would be 7 or 8 generations ahead of the actual milking cow population. So that genomic predictions 7 or 8 generations out are not quite where they need to be yet to make that work. I think we'll move beyond the DNA sequence to talk about epigenetics. Recapturing lost genetic diversity is something that we're going to have to figure out. And then, of course, the continued development of new traits. So when we think about the super cow, the genetic super cow, we are certainly a very long way from achieving the possibilities that are available to us. And I think we're not going to have one genetic super cow, we're going to have lots of them. And we're going to take different parts of different genomes. We may even take a few from different breeds and stick them in as well. So with that, thanks for your time. And my message is this: we've got a lot of work left to do, and it really is an exciting time in the area of genetics. So thank you very much.